Okay, hello, welcome to the SAMC ASTRO Time Series Methods for Astronomy course. For those of you who don't know me, I'm David Stenning. I'm a postdoc here at SAMC in the ASTRO program. So today we're doing something a little different. We're continuing having these research talks. In the second half, Tak, who's another postdoc sitting right down there, will give a talk on his research. In the first half of the course, I'm just going to give sort of an introduction to Gaussian processes, which are relevant for the second half of this class and then for next class as well. So I know that most people here are statisticians, so if this is too elementary, if I'm reviewing too much, I'll apologize in advance. It's geared more towards astronomers who might not be completely familiar with these types of methods. So just sort of for motivation, what is a Gaussian process? Why would we sort of want to use them? They provide a flexible framework to model things like curves or functions. So here we have kind of a mock example of what a planet radial velocity time series method, a radial velocity time series might look like. So last week, Becky Dawson was talking about discovering planets, typically from the dip in their light. This is another method that measures the shift in the spectrum of a star as it's moving towards or away from us due to the influence of a planet and how it interacts gravitationally. So if we could measure this perfectly, we might see something like this. And we want a way to model that. So because this is a time series course nominally, I'm going to talk about mostly examples that have a time component, such as this here. Although Gaussian processes are more general than that. They model functions in general, not necessarily just time series data. So that's just something to keep in mind. So this is to provide sort of some motivation for why this is an interesting topic to astronomers. What this chart is showing is the mention of Gaussian processes in abstracts for papers in the main sort of astrophysical journals. So I wouldn't take too much stock in the actual absolute numbers because I found them just by going to the SAO NASA ADS abstract search and typing in Gaussian processes as a word that was in the abstract. So if it wasn't mentioned by name in the abstract, it wouldn't come up. But I think it provides sort of a nice proxy to show the popularity of Gaussian processes within astronomy. You can see that going back to the mid-1980s, sort of when I was born, somewhere in this block, I won't say exactly where, there was only really 1 or 2 papers per year that were discussing Gaussian process methods, mostly coming from solar physics and people who were looking at the solar cycle and trying to have a flexible model that they could use to measure things like sunspot numbers over time or solar irradiance and things like that. And then more recently, we started seeing some people working with Gaussian processes and nonparametrics more generally, modeling spectra. And now, if you look, and I'll show some examples later, there's open source codes and other things written by astronomers to do Gaussian process modeling with astrophysical data. So it's really been within the last 5 years or so that these methods have really sort of become noticed and incorporated into many astrophysical analyses. So a normal question we might ask if you have never seen anything about Gaussian processes before is, what is a Gaussian process? I have 2 definitions here, one from Wikipedia, one from a course I took as a graduate student several years ago now. So if you go on Wikipedia, it says that a Gaussian process is a statistical distribution for which any finite linear combination of samples has a joint Gaussian distribution. That's kind of a general definition of what a Gaussian process is. A little more specifically, you can say that a GP, and not GP just means Gaussian process in case that wasn't clear. A GP on the real line is a random real valued function, y of t, which is completely determined by its mean function and covariance function. And then a key property is that any finite sample of y's as a function of t has a multivariate Gaussian distribution with the mean and covariance function that's specified for the GP. And so if this is a completely new topic to you, an excellent reference that I strongly encourage you to look at is this textbook by Rasmussen and Williams, which is made freely available online. It's kind of that the canonical text for Gaussian processes. So you can see here that gives an introduction and it goes through a bunch of examples, a lot more than we'll actually cover in this 45-minute or so course. So where did my presentation go? Excuse me, I didn't realize that would close it. OK. So this is the part where I have to ask the statisticians to bear with me. So I have kind of just a brief review of properties of Gaussian distributions, since those are obviously important for understanding Gaussian processes. I'll go through this kind of quickly, since I'm assuming most people in the room know this by heart. I probably taught it to undergrads or grad students themselves. This notation means that x, random variable x, follows a normal or Gaussian distribution with mean mu and variance sigma squared. It has this probability density function, which when plotted gives this nice bell shape that we're all kind of familiar with. And then if we extend this to 2 dimensions, we have the bivariate normal Gaussian distribution. I'm going to go through this kind of fast. The point I'm just trying to show here is that the sort of shape of that distribution depends on whether or not 2 variables, x1 and x2, are going to be correlated with one another. The strength of the correlation kind of determines how stretched and collapsed it is here. And then a nice property of bivariate Gaussian distributions and multivariate more generally is that not only are the marginal distributions of the x1 and x2 Gaussian, but the conditional distribution of x1 given x2 is itself Gaussian. And again, I'm just skipping this because I think everyone here is familiar with this. Well, what I really want to get to is to just briefly talk about the multivariate normal distribution, since that's what is really the key here to Gaussian processes. So kind of just extending the bivariate to the multivariate case, a k-dimensional multivariate Gaussian or normal distribution has this PDF here. And then kind of one of the key points is that if we have 2 sets of points, x1 are points that we want to predict, and x2 are points that we observe, then the points that we want to predict, given what we observe, has itself this Gaussian or normal distribution. And as we'll kind of see in a little while, that this becomes really useful when dealing with Gaussian processes, because it lets us do prediction fairly easily because we're just drawing from multivariate Gaussian distributions. So now to what a Gaussian process is more formally. So we have y is a univariate function of some d-dimensional theta. So because this is a time series course, you can think of theta as just being time. And so the theta 1 through theta m's would just be indexing time 1 through time m. I use this notation just because it's a little bit more general. So any finite collection of these y's, which would be a function of time, then has this multivariate Gaussian distribution. Here, r is a function of theta, and theta prime is a covariance function, or kernel, which is something that we specify. So a common choice is what's called a squared exponential kernel. It has this form here. Keep forgetting that if I try to point with this, it won't actually show up on the screen. So it has this form here where there are 2 parameters. Sigma squared is a scale factor, and L is called the length scale. The length scale controls what I'm calling the wiggliness of the function, which my spell check keeps telling me isn't a real word, but I insist that it really should be because it describes what it is quite well. And the scale factor kind of controls the scaling along the y-axis. So all kernels have the scaling factor, and often you'll see when the kernel is written down that they won't include sigma squared, and instead write just pull it out of here because it's just a common it's a scalar factor. So there's several types of kernels that you can use. You could give probably an entire course just on picking or constructing kernels for Gaussian processes. I'll review just sort of a couple of them, and then encourage anyone who's interested in using Gaussian processes to do some follow-up research on this. So we saw the squared exponential kernel. A different kind of kernel is a periodic kernel, and this is going to model functions that repeat periodically. This is clear by the name. It has this form here. And in addition to sigma squared, the scale factor and the length scale L, we also have another parameter p, which specifies the period of the function. And then a different kernel is locally periodic, which models components that have a periodic function, but which may change over time. So just to give sort of an example that's astrophysically relevant, you can imagine having looking at that RV amplitude signal that we looked at earlier, which looked like it was periodic and constant over time, but instead it's caused by a sunspot or something that is evolving. So if the sunspot grows, maybe the amplitude of that function increases, and if it shrinks, then maybe the amplitude of the function decreases. So it has a periodic component, but it's not constant over time. And so one thing that's interesting to note is that the locally periodic kernel just combines the elements of the periodic kernel that we just saw with a component from the squared exponential kernel that we saw earlier. And so this is one way that you can combine kernels to create new kernels or covariance functions that better model your data or capture aspects of the known physics that you think should be incorporated into your model. And so I won't click on this again because last time I did that, it made my presentation disappear. But here's a link to something called the Kernel Cookbook, which kind of reviews different kinds of kernels and their types of data that you might want to use it for, and in particular, how to combine different kernels to describe certain features in the data that you want to model. So when I was learning about Gaussian processes and kernels, I always kind of think of them from their formulas in terms of what they look like. Something I've seen common in astronomy that I think is kind of a neat idea is to actually depict the kernels sort of in this graphic way here. So we have the squared exponential kernel on the left with a scale factor and length scale both equal to 1. And then a periodic kernel on the right with scale factor and length scale equal to 1 again, and then a period of 2. So it kind of here, brighter colors indicate more correlation. So you can see that for points that have similar times, there's a very strong correlation, and then that dissipates off, given by the functional form of that kernel. Then with the periodic function, obviously there's this periodic component with a period of equal to 2, that things are correlated across times in that way. So it's when you're coding these, I find it's actually kind of nice to make these figures, because it's a nice way of checking that you don't have any mistakes. Because if you plot your kernel and it looks completely different than what you think it should, which happened the first time I did this, you know that you probably have a bug somewhere in your code. Like if you have a period of 2 and you don't see any period, then that's probably something you want to keep an eye on. So this shows draws from a Gaussian process. So one of the definitions that we discussed earlier was that a Gaussian process is a random function, or it's really a distribution over functions. And so a random draw from a Gaussian process is going to be one of these curves here denoted by a specific color. So if you follow kind of like the green curve all the way throughout, that's one draw from a Gaussian process. And so here, what I'm changing going from the top plot to the bottom plot is the value of the length scale. If you recall earlier, I said that the length scale determines the wiggliness of the function. I think this makes that very clear here. So when length scale is equal to 1, has kind of this amount of wiggliness. If you increase the length scale, it becomes less wiggly. And if you decrease it, it becomes more wiggly. So that just kind of shows you the flexibility that you can get. And this is just only looking at one particular kernel. It shows the flexibility you have with one kernel. And I'm not going to really discuss other kernels, because as I said, that's a class in and of itself. Again, these are just draws from a Gaussian process. This isn't, one way you can think of this is as sort of a draw from the prior distribution, if you think of the Gaussian process as a prior distribution on the functions. There's no data here, so it's just specifying the Gaussian process and then drawing curves from it. And so this sort of brings it back to this discussion of the multivariate Gaussian distribution before. So if we have some points that we want to predict given some points that we observe, the distribution of the points we want to predict given what we observe has this multivariate Gaussian distribution, which has the exact same form I showed before. I'm just replacing what I was referring to as sigma with r's because it's denoting just the Gaussian process. The covariance matrices formed from the Gaussian process kernels here. So if you kind of look at and break the mathematics down, what this is saying is that a mean for a new point is a weighted average of the points that we observe. And the mean of a new point approaches the value of observed point as the new point gets closer to it in time or whatever other variable it is that you're modeling. And the variance of a new point goes to 0 as a new point approaches an observed point. So if you kind of just stop and think about that for a second, what that sounds like is that it's doing interpolation. And that's exactly right. And one of the things that people use Gaussian processes for is to interpolate when you want to have some measure of the uncertainty on the interpolation. So here what I have in the top row is just unconditional Gaussian process draws, similar to what I showed it a couple of slides ago. I'm using a squared exponential kernel with the length scale and scale factor equal to 1. This is showing up here. The gray bars here denote essentially a 95% confidence band. I should also take the time to thank Tak, who wrote some of this code for a GP tutorial. And we'll go through more of this code next week. So we have some unconditional GP draws here. Now we observe some data and plot it as a function of time here. And this is just the observed data. And then once we have data, we can draw, we have conditional GP draws conditioned on the observed data. And you can see here that the means go through the observed points. And the uncertainty as measured by the gray intervals here increase away from the observed points and then decrease to 0 along the observed points. Sort of just like I mentioned on the previous slide. And so this is sort of a nice property of Gaussian processes. If you do have measurement error, you can add sort of a nugget so that the mean GP doesn't have to go exactly through the points. You might want to do that anyways for computational stability. But for now, I'm just not including those extra slight complications. So I think now is a good time to maybe just pause for a moment and kind of discuss what we're actually doing when we're specifying these Gaussian process models.
What are you sampling, if you go back to the last? So like, can you explain a little bit more how you get the actual curves you're talking about?
So from the top or the bottom?
Maybe the bottom.
Sure. So once we have observed data, we have a model for the points we want to predict given points that we want to observe. And so we can draw points. We're essentially just discretizing that space, then drawing points from this multivariate Gaussian distribution. And these kernels here kind of determine the shapes that these curves take, how wiggly they are and spaced along the y scale and things like that.
So in the previous slide, the y2 or the y1 would be the one that you're predicting, right?
Yeah. So we want to predict some points y2, which in this case could just be all the points kind of that we don't observe here, and we observe points y2 given by these black dots. Yeah, so this is mostly for Yeah, so for illustration, you can just imagine just discretizing the time and then saying, well, we have a lot of points we don't observe that we want to predict given the points that we do observe. In a real problem, you might want to do different things, but for illustration purposes, that's yeah.
So, and here you sample y1, a lot of values of y1, and I think you connect those dots in each color curve, right?
Yeah, to actually make the figure, yeah. Yeah, and then we're sampling many curves to measure the uncertainty and things like that. So any other questions on this before I move on? And the next slide is just discussing this a little bit, so this is the perfect time to ask questions. Okay. So when we're using Gaussian processes, what we're doing is we're specifying a prior on the relationship between, say, t and y of t, or theta and y of theta if it's not a time problem, time series. Instead of specifying some parameters that describe the relationship between t and y of t. So you might have heard of Bayesian nonparametrics. This is one example of something in that class of methods. It's called nonparametric. It doesn't mean that there's no parameters. As you can see that with the Gaussian processes, there's often many parameters, but we're not parameterizing the relationship between t and y of t.
So covariance matrix is defined by the inputs and some parameters like length of the process and the variability sigma kind of.
Yeah.
Then how do people usually set those values?
That's on my next slide. So I'll get to that question in one moment after finishing discussing this. So Gaussian processes are especially useful for things like prediction. I have what might be a little bit of a controversial claim that they're maybe not quite as useful for inferring things about the relationship between, say, here t and y of t. That's not strictly true, but what I mean by that is that to go back to this example I brought up earlier of modeling the solar cycle, if what you want to do is be able to predict slightly into the future or into the past if you're doing some kind of reconstruction, or the points in between that you don't observe in particular, Gaussian processes are particularly useful for that. If what you're interested in is learning something about the physical properties of the cycle, it might be a little bit more complicated to have something that's sort of interpretable popping out of these Gaussian processes. So if you want to learn, say, about the relationship between the rising time of one solar cycle and the falling time of the following solar cycle, that might be a little bit difficult to do with Gaussian processes because that sort of information isn't really encoded in them. In which case you might want to do something where you're maybe semi-parametric, where you're combining parametric relationships with Gaussian processes to model things like correlated noise. And I'll talk about that a little further on in this talk. So it's not that they're not useful for inference, but they're really useful for prediction and for modeling complicated functions for which you don't necessarily want to specify a parametric model. And so the Gaussian process prior is really something that's sort of implicit and reflects our belief regarding the functional form. So if we think that there's a periodic component or it's locally periodic, how smooth we think that function, how many continuous derivatives, things like that are things, the assumptions that we're building into these GP models that reflect our sort of prior knowledge. So to get back to Tak's question, the examples I've shown so far, I'm specifying the parameters of the kernels, things like the length scale, the scale factor. But for real research problems, we often, and I have here probably always, lack the actual information necessary to fix these parameters. So I wrote typical solution. Really, there's probably a few things you can do. the solution I typically take, so this typically refers to me personally, is to specify some prior distributions and do MCMC, or you can do optimization and find map estimates and so on and so forth. So because we have this nice multivariate framework, the log likelihood function is easy to write down. It's just this multivariate normal again. Here, C is just the full covariance matrix specified by the kernel. And then R is a residual vector. If you have just sort of a mean zero GP, then you can replace the R's here with just Y as the observed data. I have residuals because of what I'm going to show in the next slide or two, in case you want to incorporate parametric models in with your GP modeling. So one caveat that's probably important to mention is that inverting the covariance matrix is of order n cubed, where n is your number of observations, which can be slow if you have a lot of data. One thing that makes this a little more feasible is that often, depending on the type of kernel you're specifying, you have some amount of sparsity. So with I won't flip back, but when I showed like the squared exponential kernel, you can see that most of the non-zero values were just along the diagonal. So you can take advantage of routines that involve sparsity in their calculations to speed up some of the computation, if that's going to be a concern. So the reason I have residuals here is because with physics problems in particular, you might want to incorporate some kind of parametric models in with your GPs. This is an example I've seen in a few talks and found a reference for that just sort of online, which you can read this entry here if you're kind of more interested in this particular problem. But it's a case where you're generating data from a truth, which is just a linear relationship. And the noise is correlated. So you can see that for values less than 0, the points tend to lie above the truth. And for points greater than 0, the observations tend to lie below the line. So in this case, you might want to incorporate this linear relationship in with your Gaussian process and use the GP to model the noise, while also including your model that would be the linear model. So here the residuals would just be the difference between the predicted points and the line. So to kind of illustrate how some of these methods work in practice, I have just a toy example to go through. And now I guess will be the time I'll ask if people followed my email and brought laptops with that R code downloaded. If you didn't, that's OK. I'll go through the R code myself. But this is mostly in case you want to follow along or have some code that implements Gaussian processes to play around with later on in your own time. So I have this setup here where we have some model with parameters A1, A2, and A3, for which we don't know the parameters in practice, obviously. Reality is just, to make things simple, it's just this model with certain values ascribed to those parameters. So with A1 is equal to 1, A2 is equal to 1/2, and A3 is equal to 2. And so given 11 noisy observations, we want to infer the values for A1, A2, and A3. And in the process of that, we have to infer the Gaussian process parameters as well.
Is it 10 to the power t?
Yes. So if you plot that, we have some observations given by the black points. And then we have the orange curve, which is the true mean curve. So this is sort of what we want to learn from our model, because that's specified by these parameters A1, A2, and A3. And so this gives the model formulation. So I'm using a squared exponential kernel. You'll notice that this is in fact still the squared exponential kernel. It's just written in a slightly different way because I want to give prior distributions in a certain way. But you can do the transformation in between the two ways of just writing this. So kappa would be 1 over sigma squared. I pretty much just parameterize in terms of the precision instead of the variance. Here we have an extra term that is going to capture. You can use it to capture measurement error. Here it just kind of captures the random error. So delta t prime is just 1 if t equals t prime and 0 otherwise. So that's just, we'll set up essentially a matrix that has entries along the diagonal and 0 otherwise. So the sampling model is just the multivariate normal distribution with the mean given by our model with parameters contained in phi that are a1, a2, and a3, and the covariance matrix determined by our kernel here. And so I'm going to use MCMC and be fully Bayesian, so I need to give prior distributions on all the parameters involved in this model. So I use an exponential for beta, gamma prior distributions for kappa and sigma, and then flat priors on the parameters of the model. And then we're going to estimate these parameters with 1 at a time metropolis MCMC. And so this is where I'm going to ask you to pull up the R code that I sent around, and we'll kind of go through this as an example. And again, if you don't have it, you can just follow along with me here. So that's OK. Is this big enough? Can people see what's on the screen, or should I try to blow it up? OK. Is that good? Yes. Make it a little bit bigger. OK, so first we're just going to set up the toy problem. So we have our mean function. Here I'm using x's instead of t's, but it's the same function. So we have the reality is just the model with the values ascribed to those parameters. OK, and here we have functions that sort of set up the Gaussian processes. So we have one that calculates the kernel for given 2 points. And then we use that to calculate the full covariance matrix. So I mentioned this earlier, but so often you might need a nugget term, which just provides some computational stability. I know from running this in advance that I don't really need to use a nugget for this problem, but it's something to keep in mind when you're working on real problems that you might need it. You might need a small diagonal term just to make the computation work. OK. So this function draw prior GP is going to is the function that was generating those figures I was showing earlier, where it just has the curves from the GP without including any data. I don't think I actually use it in this problem, but just in case anyone is curious to play around with it on their own. Draw post GPs draws the conditional Gaussian processes conditioned on the data. So these functions, draw prior GP and draw post GP, are mainly just used for plotting. It's not what we're going to use to actually be fitting the model. That involves the earlier functions. To calculate the covariance matrix. And then here we have the function that just calculates the log posterior distribution. So as I keep saying, one of the nice things about Gaussian processes is that because it's essentially we're just drawing from a big multivariate Gaussian distribution, the the log likelihood and therefore the log posterior is pretty simple to write down. We're calculating the covariance matrix, and then we just have the prior distributions and then the form for the log likelihood. OK, so that is almost all our functions. Now we just have the Metropolis Hastings sampler. So as I mentioned, we're going to use one at a time Metropolis sampler and just update these parameters. OK, so now all the functions are ready, and I'm going to actually start running the code. Whoa. That is very tiny. Huh. I think that has to do with the fact that I have this plugged into the HDMI. So this is just the figure I showed right before I stopped showing the slide. So the black dots are the observed points. The orange curve is the true mean curve. So I didn't realize that the labels would shrink so much. And now we can actually run the Markov chain Monte Carlo. And I've kind of pre-adjusted it to give good step sizes, so we don't have to, play around with that all for the rest of the afternoon. So it'll run for 20,000 iterations, which you can see is fairly quick. We're already at 15,000. OK. So we're doing MCMC, so we should do some kind of diagnostic to see if our chains are converged. Really, you should run multiple chains and do something like the Gelman-Rubin statistic. Because I'm doing this in real time, I'm not going to do that and do something which you shouldn't really do in practice, but it is OK for the purposes of just demonstrating the results in a class. So these are the trace plots. We can see that they look fairly good. I say if you're publishing, run multiple chains, do Gelman-Rubin. For this kind of quick 5-minute example, we're just going to look at the trace plots. So what we're interested in were the calibration parameters, are those A's that were involved in the model. So we can look at the margin distributions and see if they're kind of the margin posterior, see if they're capturing the true values. Again, sorry that you can't read any of the numbers. This is A1, A2, and A3. The red lines give the true values, which are showing up better on my screen than here. So the red line for A3 is here, here for 2, and then here for A1. So you can see that we're doing a fairly good job of recovering those parameters.
Have you plotted these against like the priors that you put on the parameters?
So I'm using flat priors, so
Okay, right.
yeah, so no. Normally that's a good thing to do, and I encourage people to plot their priors and make sure that they make sense. In this case, I'm just assuming that the A's are uniform over a range, so it doesn't give us any additional information to plot them. In fact, they're not even, yeah. So what we actually want to see is whether we're kind of recovering that true underlying model with this, meaning that the model, once you plug in, we have many samples of A1 and A2 and A3. We can plug all those through our model and see whether or not the posterior curve kind of matches the true curve. Oops. Where did my plot go? Oh, come on, this is the last bit. I'll switch back to my slides now because I have this in there. So you can actually see the labels. OK, was anyone actually able to follow along and run the code on their own? Yes? OK, good. I personally didn't include any kind of libraries or anything else, so it should be fairly straightforward to reproduce. You can play around with different kernels and things like that pretty easily just by swapping them in and out of those various functions. So this is what the trace plot should look like if we could actually read all the labels, the marginal posteriors. And here is sort of our final result. So we have the observed points, and then the orange curve is the true mean curve. The solid blue curve is our prediction, our predicted mean curve. That's the posterior mean. And then it's the function formed by plugging in all the different values, right, 1, A2, and A3, and then taking the mean at each point y, so at each point here, just to be more precise. Then the dashed lines give the 95% credible intervals. So as expected, when we don't actually have any more data, our intervals kind of blow up, which is what we expect. But in the space where we do have data, we're maybe missing some features of the true curve, but overall we're doing a fairly good job, especially if you look at the credible intervals in terms of capturing that. So this was trying to just give a sense of something that you might want to do for an actual physics problem, because often you might have some kind of underlying model like this. But one of the areas I do work in is in uncertainty quantification, where you have kind of these big, expensive computer models that you can run and get outputs given certain inputs, but you can't necessarily write down the model in any kind of analytical form or run it particularly fast. But this is one of the tools that people use to be able to fit models like that, because you just really need to know the outputs for various inputs, and then you can model those in this Gaussian process framework and try to do some kind of inference about the physical model, as well as be able to make predictions at unobserved points.
But in this toy example, you assume that you know the true functional form of the process.
I did, yes.
So what happens if you don't know it?
So you can use Gaussian processes if you don't know the true functional form. So when I was the first bits I was talking about weren't involving any kind of underlying model. This was mostly just to say that you don't have to completely throw out your functional forms, your parametric models, if you do have them. In which case, I guess it would depend a little bit on what you're trying to do. If you don't have a functional form, you're obviously not trying to infer parameters of that model, because if you don't have a model. So you would more likely be trying to do something like prediction, in which case that you don't need necessarily to have a functional form. For the underlying model, you actually have functional forms for the Gaussian process.
I think if you don't know the functional form, then in this case it may be the same as your previous prediction, like bubble.
Yeah, if I didn't allow for any kind of measurement error or nuggets, then it would kind of go through all these points, and the uncertainties would grow and things like that. Yeah.
But maybe it would still take the same shape or something.
Yeah, you can get things that it's hard to say know exactly what would happen in this model without having run it. Although that's a thing that would be interesting to try, is to just get rid of the physical model and see what pops out of the GP. You can capture. Gaussian processes are very flexible, as I mentioned, with the choice of kernel, and then with the parameters within that kernel that you would fit. They're really flexible, so it wouldn't surprise me if you could capture something similar if you're in terms of like having two plots side by side and saying that these functions look the same. I think then the benefit of including a model or not really comes down to what questions you're asking, what you're trying to answer. If a lot of times physicists and astronomers, cosmologists are interested in knowing parameters of those models, in which case you obviously need to include them. If you're doing if you don't have a model, if all my work has been in astronomy, so I can't think of a good example off the top of my head, but if you're predicting like stock returns, say, you might not necessarily have any kind of model that you want, or well, maybe you would want, I would love to have a model for stock returns, but you don't have a model for stock returns, but you want to be able to predict something maybe one day into the future, in which case you just want your Gaussian process model to be doing well. You don't necessarily need to have some kind of underlying knowledge about what like the true function really looks like.
So you could theorize a true model, but maybe you don't really have a good idea of what that its functional form would look like. So I'm wondering, is there like, maybe you just use like the density for the normal distribution as like your canonical functional form, and then try and like fit those parameters to the data, and maybe you would still get something in the same shape. I don't know. Maybe.
I mean, this one looks we're not really fitting a density to this, so we're modeling the function. So yeah, when I talk about the multivariate Gaussians, it's that the joint distribution of all these points is multivariate Gaussian, but it doesn't mean that when you're plotting the function like this, that it would have any kind of a bell shape. We're not looking at the joint distribution.
That's okay. That's fine.
Yeah. Yeah. So I guess my general comment on that is that if you are dealing with a situation where you want to learn about a physical model that you have, like in cosmology, for instance, or in most examples I can come up with come from the physical sciences, because that's where I've done work in. Then you might want to do something similar to what we've done here, where we're including that. If you don't, then there's no reason to make unfounded parametric assumptions unless you for some reason need to know those parameters. But one of the nice things with Gaussian processes is that they're flexible, and you don't need to parameterize the relationship between, well, here between x and y, between t and y of t. So I don't think you should maybe hamper them, so to speak, by making parametric assumptions unless they're well-founded from some kind of model of reality that you believe or know to be a good approximation. So this kind of concludes the introduction portion of this talk. The remaining slides that I have are mostly discussing just a few examples highlighting work that people involved with the SAMC program have done that use GPs. It's most certainly not exhaustive. I don't know what everyone's working on, and I'm sure more people are using GPs than I'm mentioning here. But it just shows a few examples that I happen to be familiar with. So this first example comes from Ian Chikala. He's, I believe, a postdoc at Stanford now. So what he was interested in doing here was using a Gaussian process to model spectra. And one of the difficulties with that is that while there is a physical model in this case, that gives that, which is the red curve here, it's known that the model isn't necessarily a good approximation to reality, and in particular, there are certain spectral features that aren't captured by the model. And so what he was doing was to carefully construct Gaussian process kernels that sort of learned this mismatch and incorporated that into the final analysis. So you can kind of see that here, where there's more mismatch between the data and the models, the uncertainty in the GPs grows. So it's not fixing it, but you're at least accounting for it, and you know that it's there. Again, I'm not going to click on the links because you saw there earlier that makes my presentation disappear. But if you are interested in any of the examples I'm talking about, these are hyperlinks here that you can click on and get the archive versions of the papers. Another example also coming from Ian. This is something that he's been doing while at SAMC, looking at spectra coming from binaries. So you observe one spectra, but you know it's coming from two stars. What you want to be able to do is disentangle the components from different stars. So this is just sort of a synthetic example, but taking sort of this red curve and the blue curve, combining them to make the black curve, and then drawing noisy observations from the black curve. So this serves as input, and then seeing whether or not you can split it into the blue curve and the red curve that were the inputs. And you can see here that he's doing, his group is doing a fairly good job of that. These are just, I'm assuming that these are residuals down here. Another example we saw last week, but in case you weren't there or just want a reminder, this comes from Becky Dawson. And what she's showing is that if you account for correlated noise in your observations, which means that she ends up using a Gaussian process model to account for that correlated noise, you end up doing better for recovering parameters from these synthetic, they call them injection tests, than if you assume simple uncorrelated Gaussian white noise. So the black shows the uncorrelated assumption. The red shows when you're assuming that there's correlation using a GP. And you can see that there's some cases where the GP is doing much better in terms of capturing the true values as denoted by the black vertical lines. In some cases, they're not too different, but if what you're interested in is looking for new planets, rare events, maybe you do care about the cases where you are getting it wrong by making a wrong assumption about your noise. Lastly, this is sort of a preview of what David Jones here will talk about next week. It's a project that he and I have been working on together, mostly him for the Gaussian process modeling. But what we're interested in doing is taking time series of spectra from stars that we know have a star spot on them. So it's a dark spot on the star's surface that's rotating around. Why this is interesting is because the signal from that rotating spot can mimic that of a planet. So if we want to be able to find planets through this radial velocity technique, we need to be able to disentangle the signal from stellar activity, things like star spots, from that of planets. And so we craft features from the time series of spectra using things like PCA or diffusion maps, which is the part that I've been focused on. And then this is showing our model for when there's no planet, and we have a model when we do have a planet. And I won't say too much about this because David's going to talk a lot more about this next week. So this is just kind of a preview and a way of saying that Gaussian processes continue to be popular in astronomy, as shown by the fact that there are several groups just at SAMC using them for various different kinds of modeling and different kinds of scientific problems and goals. So if you want more information, as I mentioned before, the canonical reference is Rasmussen and Williams. And if you're an astronomer and interested in kind of in implementing some of these models, Dan Foreman-Mackey, who's been somewhat involved in the SAMC program, has this really nice code written in Python. So I know astronomers love to use Python. Statisticians use R. Wish we could agree, but we don't. So if you're a Python user, I encourage you to kind of check out Daniel's code and maybe go through some of the tutorials to learn more about these models and how they're implemented. Well, and then my last reference was a link to, I'll pull it up because I have my email too. To Ian Jikala's code for Starfish, which was the code that was doing the modeling that I showed a few slides ago here. So if this is sort of an interesting problem, and you have spectra of your own that you want to model, and you are worried that you might have mismatches, you should check out Ian Jikala's code. I think it's pretty cool. And then finally, if you want to contact me for more information, I have my email addresses here. I think there's probably a couple more related to Duke floating out there, but these are the best ways of reaching me. So we're a little, actually, I don't know the time.
It's 5:30.
Oh, perfect. So if there's any questions, well, you can ask me now. After the break, we're going to switch to talk is going to give a more research-focused talk. So any general questions on GPs, we should address now, I suppose. Yep. OK.
Just one more question. Like, whenever you're using a Gaussian process regression, if there is a trend, then you cannot model it with Gaussian processes, right? Like, if the distribution is not stationary.
I'm not expert enough to answer. I think that you.
Yes.
I'm not sure. Maybe we should talk about that.
It depends on the kernel.
Yeah, they're non-stationary kernels, I thought, but I'm not an expert in that area, so I don't want to say one way or the other.
Because these popular kernels guarantee stationary.
Okay.
But I have also no idea about non-stationary kernels.
I think we have a talk on non-stationarity coming up eventually. I think you're giving. Were you giving that talk or?
No.
OK. OK. Any other questions? Nope. OK. Well, thank you for coming and participating. I guess we'll take, let's say, a 15-minute break, then come back here for talk.
Thank you for coming to the second session. I'm going to talk about strong lens timeless mission as an example of using Gaussian process to solve some astronomical problem. I will first introduce what the strong gravitational lensing means, and with some description of the data, I will introduce the model. And based on this model, I will come up with two estimation methods. One is Bayesian, and the other is frequentist optimization-based method. And I prepared 3 examples, and the last example is based on some R tutorial. OK, let me first introduce strong gravitational lensing. In this video, you see images of 2 stars. But actually, these are the same star. What happens is the strong gravitational field of this intervening galaxy splits the light into 2 images of the distant star. And because the length of each path can be different, their arrival times can differ. So we call this difference between their arrival times the time delay. And this is an image we can see through the telescope. OK, here's another figure that describes a strong gravitational lens. This intervening gravitational lens bends the light emitted by this distant galaxy. And from our perspective, we see the images of the same star around the lensing galaxy, because we can't see directly the quasar, the distant galaxy. So here we see 4 images of the same star in the lensing galaxy. And this is a snapshot that we can see through the telescope. If we measure the brightness of these lensed images over the time, then we have 4 time series of brightness. And we use these 4 time series data to estimate the time delay. And time delay is useful because astrophysicists use time delay to infer some cosmological parameters. For example, the Hubble constant that measures the current expansion rate of the universe. And time delay can constrain some parameters in this equation of state of dark energy that characterizes the accelerating expansion rate of the universe. So if you have a question, please ask me whenever you want. So here I prepare a simulated data set of a doubly lensed quasar. Quasar is a very luminous galaxy that hosts a supermassive black hole at the center. That is actively accreting. In this figure, the horizontal axis represents the observation time, and the vertical axis indicates the magnitude. And the magnitude is an astronomical measure of brightness, which is on log scale. At each observation time, we measure a pair of brightness from two lensed images of the same star. So if we measure these brightness over the time, then we obtain two time series. So the data have four variables observed at n observation times, the observed magnitudes of each time series, and the standard deviation of that measurement. So these measurements are displayed by the half length of the vertical lines near symbols. So our job is to estimate the time delay, the shift in the horizontal axis between two time series. For example, this V-shaped valley in the red time series appears earlier than the V-shaped valley in the blue time series, meaning that blue time series is lagging behind by about this amount of time. So we want to estimate this amount of time using a statistical model. So I set up a statistics-based model to estimate the time delay, and it has several assumptions. The first assumption is that there exists unobserved underlying light curves that represent true magnitude in continuous time. You might guess that this continuous curve is a realization of the Gaussian process. I will explain that later. And these red and blue dashed curves are these latent true curves. And I use capital X of t and capital Y of t to denote the n true magnitudes on these curves at n observation times. So these are discrete realizations of a continuous time curve. And the second assumption is the most important assumption, which is called a curve shifting assumption. This is saying the blue curve is a shifted version of the red curve by the time delay in the horizontal axis and by beta naught in the vertical axis. That means if we move the red curve by the time delay to the right and by beta naught downwards, then the red curve would exactly overlap with blue curves.
What are the states of this model?
State is a realization of the true magnitude state. State is the observed value.
Okay.
And this first assumption means these observed magnitudes are generated by the underlying latent true values. And in the underlying level, these true magnitudes have some process described by the Gaussian process.
But the data points are just like the observations conditional on like what state you're in, right? Does that make sense?
The state is here the observation time.
Okay. All right.
Okay.
So from here, we assume some distributions for the data. As the first assumption in the previous slide says, we assume that the observed magnitude follows some Gaussian distributions centered at the unknown true magnitudes with standard deviation equal to the measurement standard deviation. And the second assumption in the previous slide says we can replace this capital Y with the shifted version of capital X. And by doing this, we don't need the capital Y anymore because we can explain all the observed magnitudes using just one curve, one continuous time curve, X, capital X. And by doing this, we can have the time delay as a parameter of a probability distribution. That's why we can estimate the time delay using probability distribution as a parameter of the probability distribution. Okay, Gaussian process. So we assume that the curve, the true latent curve, is a realization of the Gaussian process. I'm focusing on specific Gaussian process, which is called Ornstein-Uhlenbeck process. And astrophysicists usually call this process as damped random process. And many astrophysicists have used this Ornstein-Uhlenbeck process to describe the quasar variability because they empirically show that the Ornstein-Uhlenbeck process describes the stochastic variability of the quasar Lie curve very well. And this Ornstein-Uhlenbeck process is based on this stochastic differential equation, where tau is a mean reversion time. That means when the process deviates from the overall mean, mu, then tau indicates the time for the process to come back to the overall mean. So for example, suppose Gaussian process looks like this. And this is the overall mean. And tau is the time amount, the average time of these intervals. And this tau is corresponding to the length of process that David Stenning described in the previous slide, like it was small l. And sigma is the short-term variability coming from this Brownian motion. So capital B of t is Brownian motion, and the randomness and the short-term variability cause some variation in the process. So the modeling the capital X, the true magnitudes, using a Gaussian process means that we define a multivariate Gaussian distribution of the finite number of the magnitudes. For example, so we have n true magnitudes for one time series, and another n capital X true magnitudes for the shifted observations. So using a Gaussian process means we assume that these finite number of magnitudes follow a huge multivariate Gaussian distribution. In this case, the center is the overall mean mu, and the covariance matrix only depends on the input values, which is the time in this case. So each element is defined as an exponential function of kind of the observation cadence and some parameters, which are called hyperparameters that David Stenning mentioned. And we call this specific form of covariance function as matter 1/2 covariance function. So we have set up the model, and here we have two choices. If we use some prior information for the unknown parameters, then we can set up some Bayesian model deriving the posterior distribution. If we don't want, or if we don't have such a prior distribution, then we can derive a frequentist method like optimization, MLE, or something like that. So I will explain these two methods, and the first one is Bayesian approach. And let me explain how we set up some prior distribution for the unknown parameters using some astronomical knowledge for some informative prior. So as a statistician, I may concern about posterior propriety because if we use some improper flat prior distribution, then although it is non-informative and convenient, sometimes it leads to improper posterior distribution. That means the integration of the posterior distribution will go to infinity. So, whenever we use improper prior distribution, we should check whether this integral is finite. Otherwise, this posterior distribution is not probability distribution. But the problem of this model is that the likelihood function is very complicated because it is shifted to Gaussian distributions. So in order to avoid the posterior impropriety, so we decided to use all the proper prior distributions. But astrophysicists may not care about this posterior propriety. They may care how we use some astronomical knowledge to set up the prior distribution. So
Do there exist like conjugate priors in this case?
I use some conjugate priors, but the others are not conjugate priors. So yes, some conjugates. I'm using some conjugacy, and I will explain that. So we use a uniform prior distribution on the time delay with finite range. If we have some prior information to constrain this time delay, for example, if we have some knowledge about the mass distribution of the lensing galaxy and the location of the quasar lensing galaxy and the Earth, and if we know how fast this quasar is getting far away from us, then we can use some physical knowledge to constrain the range of the time delay. If we don't have such information, then we can still use this kind of range. And this range guarantees that no matter how much you move the time series data, there is always at least one data point making these two time series overlap. And we use a uniform prior distribution on the overall mean of the process using this specific range. And the reason we set up this range is that the brightest object we can see is the sun, and the magnitude of the sun is negative 26.74. So this is fairly large range on the negative side. And the faintest object that the Hubble Space Telescope can identify has magnitude 30. So this range reflects on some technical limitation. And actually this is practical range. And we assume a uniform prior distribution on the magnitude offset, the shift in the vertical axis, because magnitude offset is the difference between two magnitudes. Since one magnitude should be within this side, practically, so difference can't be outside of this range. The most difficult part was setting a prior distributions for some positive parameters. Because if it is location parameters, then we can use some uniform prior distribution like I did before. Some people use inverse gamma distribution for the second level variance component because this is, as you said, conjugacy, computationally convenient. But our team came up with another meaning of using inverse gamma distribution. That is to set up a soft lower bound of the random variable. So for example, suppose X follows inverse gamma A and B distribution, and the probability density function is looking like this, and the mode of the distribution is B over A plus 1. So let's think about what happens if X goes to infinity. So if X goes to infinity, then the exponential part goes to unity, and the power law controls the right tail behavior. And if X goes to 0, then the exponential part dominates the probability density function, so it decreases exponentially fast. So here is, this figure is based on inverse gamma 1 probability distribution. And the mode is just 1/2, because this is B over A plus 1 is 1/2. And for this random variable, it is extremely difficult to take on some values much smaller than the mode, because this probability density function costs up the likelihood, exponentially costs up that kind of probability. So that's why we think setting an inverse gamma prior distribution is to set a soft lower bound of a random variable. So random variable X for X, it is really difficult to have some values much smaller than 0.5. So let's think about why we need these soft lower bounds for these parameters. So sigma is a short-term variability. That means if we have some process like this, then sigma represents the half length of the variation. So let's think about what happens if sigma goes to 0. Much, much smaller than our measurement error. So what I'm saying is, when this is the short-term variability of the process, if we have some measurement error, something like this, what happens is we will observe some white noise because the measurement error is too big, much bigger than the short-term variability. So in order to prevent this case, if the observation is white noise, then there is no way to find the time delay by matching some meaningful fluctuation patterns. So we need to set up some soft lower bound, and let's think about the tau, the time scale of the process. So if tau goes to 0, that means if tau is much shorter than the observation cadence, this time we will also observe some white noise because this is too wide to reflect on some underlying fluctuation patterns. In order to have some meaningful data, our observation time must be shorter than tau. In that way, we may observe some meaningful fluctuation patterns of the underlying light curve. So we have some motivation to set up some soft lower bounds of sigma square and tau. So we set up these specific choices because we realized that McLeod et al. In 2010 analyzed about 9,000 quasar light curves, and they provide some 9,000 estimates of sigma square and tau, and we realized that our choice is much smaller than the smallest estimates out of 9,000 estimates. So we set up all the probability distributions. So we can derive the full posterior distribution by multiplying probability density functions of all the observed data, which is multivariate Gaussian with diagonal covariance matrix, and the probability distribution of latent data defined by Gaussian process, meaning that this is a joint multivariate Gaussian distribution. And we also set up the prior distribution of the unknown parameters. And it is not difficult to derive the Gibbs sampler, updating a block-wise parameter at each iteration. However, actually our team thinks Bayesian method has its own pros and cons. Bayesian method provides a complete summary of all the unknown parameters, including their joint distribution. However, this Bayesian method is not efficient if there exists some multimodality. So in the presence of multimodality, we should have something else. So that's the profile likelihood function. A profile likelihood function also focuses on one parameter, the parameter of interest, with the other parameters maximized out. It is defined as a maximized likelihood with respect to the parameters that we are not interested in. And in our article, we have shown that this profile likelihood is asymptotically proportional to the marginal posterior distribution of the time delay. This profile likelihood has the opposite pros and cons. It is simple to implement because profile likelihood is a function of a single parameter. So we can just draw a curve of the range of our interest. So it is easy to find some multimodal behavior of the time delay. However, this calculating profile likelihood curve function can be computationally expensive because we need to evaluate the profile likelihood on a fine grid of values of the time delay if we want to have some finer curve. Also, this profile likelihood doesn't provide some information among the relationship among parameters because it maximizes out the other parameters. Since Bayesian method and profile likelihood approaches complement each other, we mix them to estimate the time delay. First, we drew a profile likelihood curve of the entire range of interest. And if we find some multimodality, we initialize our Bayesian method near that mode. So this is the first example, and let me introduce the time delay challenge. The time delay challenge is a blind competition held by 8 astrophysicists from 2013 to 2014. The goal was to improve the current estimation methods for the era of the Large Synoptic Survey Telescope. You may have heard a lot of times, of this LSHC a lot of times this semester. And the organizers generated 5,000 data sets with some time delays. And 13 teams blindly analyzed these 5,000 data sets. And we reported our estimate of the time delay with uncertainty. So here is the result of the last stage. And the organizers used 4 criteria to evaluate each team's performance. F is the proportion of data set we could analyze. So here our performance is denoted by baby blue triangle. And we analyze the second most data sets. And P is precision. In statistics, this precision means, this is the terminology of astrophysicists. So P means coefficient of variation. So here we achieve the best precision. And A means accuracy. But in statistics, A is bias. Chi-square is the square standardized residuals, the average of them. So if the gray area, gray boxes, here and there, gray boxes represent the goal of this, the blind competition that the organizers wanted to achieve. So if we see the accuracy in chi-square, we are in we achieve the goal of the accuracy and chi-square. And among these methods that achieve the goal of accuracy and chi-square, we achieve the best precision, although no one achieved the goal of the precision level. Okay. So here is one example of the simulated data sets. And using this data, we obtain the profile likelihood curve of the entire range, feasible range. And then we exponentiated this profile log likelihood curve. And we find a dominant mode of the space. So we initialize our Bayesian method near this mode. So here I magnified the mode, the dominant mode. And here I display the posterior sample of the time delay. And there, the red lines, the vertical red lines, indicate the previously blinded time delay. Here I also summarize the posterior mean of the time delay and posterior standard deviation obtained from Bayesian and profile likelihood methods. And these are very similar because their shapes are very similar. At the time, we didn't know the true value, so we checked whether our estimates are reasonable or not by shifting the blue time series by our estimates. By time delay to the left and by beta naught hat to the outward. After the shift, it seems like the fluctuation patterns match very well. So we think, okay, this time delay estimate seems very likely. And we also check our model because Gaussian process is very good at prediction. So these gray areas around the light curve, it represents our prediction based on Gaussian process. So it seems like the gray areas are encompassing the observed light curve very well, meaning that our model is appropriate to estimate the time delay in this case.
The gray is filling in the points you don't have, you're saying, or what is the gray? How do you?
So gray. Do you remember in David's slides, he's talked about x2 given x1. So gray area is the sample of these x2. So the difference between David's talk and my talk is that he connected all these predictions to make it like a curve.
Ones you already have,
Sorry?
you're resampling ones that you have. Right?
Yes, I'm sampling maybe I think here 10,000 times. And then I didn't connect the curves, but I just plotted these predictions in gray dots. So it looks like the area. So if we connect those predictions, then it may have 10,000 curves in different colors in his lecture, if we think about his lecture. Here is a real example. This is quasar Q0957 plus 561, which is observed at the United States Naval Observatory for 3 years. And we ran our model first implementing profile likelihood curve, and we implement our Bayesian method near the mode. Here, the approximation is not that good, but actually profile likelihood is catching all the possibilities like the small mode and all the other 3 modes. And here we check our estimate and we check our model here. So here I display some numerical summaries, including the historical estimates. And we use the smallest number of observations. But we could have some consistent estimates to the historical estimates with comparative measurement, or time delay standard error. This is partially because our observation is the most accurately measured. So here, we display their historical estimates by vertical dashed lines. So this second figure shows the advantage of our approach. All these historical articles report their estimates and their standard errors. It's just 2 numbers. Since our work provides the entire distribution, we could see all the possibilities with their corresponding the size of each mode. So our approach could provide more informative estimation result, inference result. Okay, my last example is based on the simplest time delay estimation model based on this R package called time delay. Okay, let me run that. Okay. So here we install the time delay package. And in order to use this time delay package, we need to load this package by typing library time delay. And I load the data, the simple data of this package, included in this package. And the data looks like this. So the first column is about the observation time. And the second column shows some observed magnitudes of one time series and their corresponding measurement error. And the first column indicates the observed magnitude of the other time series and their measurement error in the last column.
Where did the measurement error come from?
Measurement error comes from the telescope because telescope knows how accurately.
You know it.
Yeah. So I think it's not true that in many fields, measurement errors are not known. But I think this is very unique field because telescope is very rigorously calibrated to calculate the measurement errors. Okay, let me plot let me plot the data so that we can have some idea of how the data look like. Oh my. Okay, maybe you can run your on R. Can you see some?
If you go to display settings.
Okay, display. But I think this is visible.
This is okay for you?
Yeah,
Okay.
I think it's fine. This is the only figure I have. So you see one time series is here and the other is here. I hope you can see. And we are trying to find the time delay that matches the shift very well. So here we run our Bayesian model. Data flux. And then we just display the time delay. Okay. It took 15 seconds. So this is the posterior distribution of the time delay, and I denoted the true value of the time delay by red vertical line. Okay, let me conclude this talk. Okay, I think time is okay. So let me introduce the second blind competition to be held soon. I mean, early this year. So this time, organizers want us to develop some multivariate estimation method. Multivariate, I mean, what I'm saying is, so LSST will use 6 optical bands to monitor the sky. That means for each quasar, we will have 6 pairs of light curves, because for the same quasar, we will have 6 images at each observation time. And for each image, we will have a pair of time series. So in this case, what we need is a multivariate Gaussian process to model these 6 multivariate time series. So the organizers will generate more than 5,000 quasar systems, and each quasar system will have 6 bands, meaning the 6 pairs of time series, and each time series will be composed of 150 observations. So it is really great opportunity to learn some time series analysis. And actually, this time delay estimation is a specific feature of the time series analysis, very specific feature. And you can find the information of time delay challenge from this website. And thank you very much. And do you have questions or someone online? Okay. Thank you very much.